Every time you look at the landscape of modern AI, the message is always the same. It's all about scale, complexity.
Massive data centers.
Exactly. Massive data centers, the latest, most expensive GPUs. The barrier to entry for running a powerful large language model just feels like it's getting higher and higher. Okay,
Okay.
let's unpack this. We got our hands on source material about a deeply fascinating and really counterintuitive project that just takes a sledgehammer to that entire assumption.
Right.
Our mission today is to dive into how a developer managed to port and run a modern LLM, we're talking Llama 3.2 3B, on a 10-year-old consumer gaming device.
The original Nintendo Switch.
The Nintendo Switch, it's just wild.
It really is an engineering feat that's kind of built on defiance.
Yeah.
I mean, the initial reaction from pretty much everyone was total skepticism.
You'd have to be.
Yeah. The standard device. And, the funny thing is, even the model's own output suggested the Switch was just hopelessly unsuitable.
And the specs totally back that up. I mean, we're talking about a device with some serious limitations.
Oh, yeah.
Only 4 gigabytes of total system RAM. And a GPU that was designed for, what, rendering Mario Kart? Not for complex parallel processing.
It's built for a completely different era of computing.
It is.
And yet the core mission was to prove all of that doubt wrong.
Hmm.
And the amazing result is that they did it.
They actually succeeded.
Through this intense, weekend-long gauntlet of software hacks and system tuning, they got a 3.2 billion parameter model running at a clip that is, well, against all odds, it's actually usable.
Let's figure out how they managed to turn this beloved handheld console into a tiny little AI accelerator. To start, we have to look past the plastic shell of the Switch and look at the silicon underneath. At its heart is the NVIDIA Tegra X1 chip.
Which is old.
It's so old. It was announced back in January of 2015, so it's a true decade-old piece of tech, originally meant for, tablets and cars.
Right.
It has 4 GB of RAM, and this is the important part, 256 Maxwell CUDA cores.
And those CUDA cores, that's the key. That is the one thing that makes this entire project shift from just a weird idea into a real possibility.
The secret sauce.
The secret sauce that powers the entire AI world. The whole project hinges on NVIDIA's unified compute platform, CUDA.
So because this old Tegra X1 chip supports the CUDA architecture, all the highly optimized code that's designed for today's, massive AI accelerators should, in theory.
In theory, yeah. It should be compilable, and it should run on this decade-old mobile hardware.
That uniform compatibility is really the story here, isn't it? It suggests that if you buy into the NVIDIA ecosystem, you're buying an architecture that doesn't just get thrown away when the next generation comes out.
Precisely. And the source material makes a really important point here. NVIDIA still supports desktop Maxwell GPUs that were released almost 11 years ago.
Wow.
This backward compatibility is, it's just revolutionary in a field that's obsessed with the bleeding edge. And it's what allowed a developer to even think about linking a modern AI toolchain to a chip designed back when Windows 10 was still new.
Right.
Contrast that with competitors who often have to rewrite their entire compute stacks just to support new, expensive hardware.
So the hardware was, let's say, willing, but the operating system, the software infrastructure, was basically fighting this modern code tooth and nail.
Oh, completely.
You couldn't just drop a huge AI program onto the Switch and expect it to run. It needed a proper foundation first.
And that foundation required just a heroic level of open source reverse engineering. We have to give a huge shout out to the community effort from the SwitchRoot organization.
The source material calls their work Herculean.
And it really was. They managed to create a fully functional, stable port of Linux for Tegra, or L4T, for the Switch.
Which gave the developer the OS they needed, something like Ubuntu 18.04.
Exactly. And crucially, this wasn't just, a command line. SwitchRoot made sure that everything works. The Joy-Cons, the touchscreen, HDMI, out. And most importantly, it enabled a working CUDA development environment.
That is a massive hurdle cleared, just to get a stable base. So once they had Linux running, they could finally start bringing in the actual AI tools.
Right. And for that, they used 2 really indispensable open source tools from the local AI scene. First, llama.cpp.
Which everyone knows. It's the go-to for running LLMs efficiently on consumer hardware.
And second, the core computational engine that powers it, which is called GGML.
And what is GGML, fundamentally?
GGML is the crucial library inside llama.cpp that does one thing really, really well. High-speed matrix multiplication. This is the bedrock of all AI inference.
Okay.
The model they picked, Llama 3.23b, was run in a highly quantized state, which means its huge file size was aggressively compressed so it could even hope to fit in this switch's memory.
So the goal was to take this modern compressed math engine and just force it to cooperate with the decade-old drivers and compilers on the Linux install.
And that's where the project stopped being an interesting theory and became an absolute nightmare.
This sounds like dependency hell.
It was.
Here's where it gets really interesting. The developer basically documented this whole process as this series of complex technical detective puzzles that took up an entire weekend. It was just one cascading incompatibility after another. What was the first big wall they hit?
Well, the first major battle was the CUD version itself. The Linux environment, because it was so old, only came with CUDA 10.0.
And the new code needed.
The new GGML code needed features from CUDA 10.2. Specifically, it needed access to more advanced math libraries for those matrix calculations we were talking about. It was like trying to fit a modern engine into a vintage car.
How'd they solve that one?
Luckily, there was a community patch available, so they could update the core CUD install from 10.0 to 10.2. That solved hurdle number one.
But that just led them straight into the next problem.
Straight into the next one, the compiler.
The C++ language dialect issue.
Exactly that. The modern GGML framework was written using features from C++17, but the old Tegra environment was stuck with a compiler that, just didn't know what that was.
It's like it was speaking a different language.
Totally. It would just throw these cryptic errors. So the developer had to deliberately tell the build system to basically lie about the code's age, just to get past those first errors.
That's classic legacy hardware stuff, isn't it? Forcing things to downgrade their requirements to match the old tools.
But it gets worse. Even after finessing the C++ standard, the biggest problem was the core system compiler, GCC.
Ah.
The Ubuntu version, they had only shipped with GCC 7, an ancient version. Both CUDA 10.2 and the modern LLM backend needed GCC 8.5 or newer.
So they couldn't just download a new package because the operating system was too old. They had to. They had to build it themselves.
They had to beat it the hard way. They couldn't just download a new compiler. They had to build a new compiler from source code.
Source.
And not just any source code. They needed a specifically patched version of GCC 8.5 that had critical updates for the ARM64 architecture, which is what the Switch CPU uses.
Wait, hold on. They had to compile an entire compiler, this hugely complex piece of software on the Switch's, and I quote, anemic CPU, just to prepare the environment.
Yes. And the developer noted that this process on that little processor took a couple hours.
A couple of hours. Just for tooling. That gives you a real sense of the patience required just to get the system to a point where it could even begin to compile the final AI program.
And even after all that, there were still more patches. They had to make small but critical code changes to the LLM source itself, removing modern C++ features, fixing these subtle linker bugs. It was a complete technical scavenger hunt, but it ended in a successful binary.
So they did it. They finally had a compiled working llama.cpp binary. In theory, it should run the model.
It should.
They launch it and the system just throws a red card. The process was killed.
Instantly. It's that tragic, immediate failure you see in highly constrained computing. And the cause wasn't the CPU or the GPU. It was the one thing we all forget about in the age of, 64-gigabyte laptops.
Memory.
Memory. The ultimate bottleneck was the Linux out-of-memory killer, the OM killer.
Okay, let's talk about the OM killer, because this is such a critical insight for anyone trying to run AI locally. What is it, and why did it target the LLM?
So the OM killer is Linux's last line of defense. When memory runs critically low, instead of letting the whole system crash, it violently assassinates the single biggest memory hogging process to free up resources.
And in this case, that was the LLM.
That was the LLM. The quantized 3.2 billion parameter model needed about 3 gigabytes of breathing room to load up and run its calculations.
3 gigs out of a total of 4. That leaves only about 1 gigabyte for the entire operating system itself.
Precisely. And the default graphical desktop environment on Linux port GDM3 and the Unity desktop, it's built for comfort, not for memory efficiency.
So it's just eating up that critical headroom.
It was eating that 1 gigabyte and bleeding into the LLM's required space, which triggered the OM killer to strike the second they typed a prompt.
Wait a second. So the biggest bottleneck,
Right.
it wasn't the specialized GPU core or the slow CPU. It was the graphical background images and menus of the default desktop.
That's the ultimate irony.
It's the whole pivot of the story.
It is. The hardware was totally capable of the sophisticated AI math, but the graphical window manager was the real enemy. It was starving the AI of resources.
So what was the fix for that?
The final, crucial step was to ditch the heavy desktop environment entirely. They swapped it out for the super lightweight LXDE desktop and used Litium as the display manager.
And that minimalist tuning just freed up enough RAM.
It freed up just enough essential memory to let the model load and run consistently without getting terminated.
And once that final non-technical hurdle was cleared, what were the numbers? What was the performance that made this whole insane effort worth it?
So, running the Llama 3.2 3B Instruct model, the switch achieved a performance of about 3.5 tokens per second.
Which is not a speed demon by any stretch.
Not at all, but the source calls it a pretty reasonable clip for local inference. It means you can have a functional, if slow, conversation with a real AI model on a decade-old handheld console.
That's just a powerful statement about how far quantization and local AI tools have come. And there was a great anecdote in there, too, about the model helping to rescue itself, right?
Yeah, this was great. When the developer was deep in the fight with the O killer, they actually asked the LLM itself for advice on low memory management.
Ah.
And the model, even while it was struggling, it spat out some hallucinations that were just close enough to the real fixes. It mentioned things like swappiness and O scores that it sent the developer down the right path on Google to find the real solution.
A little bit of AI self-help. That's fantastic. So what does this all mean?
Well, I think this deep dive really shows that old consumer hardware can be resurrected for modern tasks, as long as it supports a legacy compute platform like CDA. It's a testament to the monumental utility of open source projects like llama.cpp and ggml.
Right.
They make these quantized models so flexible that you can squeeze them onto devices that nobody ever intended them for.
It also shows that the real victory isn't about setting speed records. I mean, a modern laptop CPU could probably run this faster. The success here is proving the principle.
The principle of accessibility.
Exactly. Accessibility to powerful local AI is now more about software ingenuity and memory optimization than it is about having the most expensive graphics card. The bottleneck wasn't the AI core, it was the graphical overhead.
Right. And this whole conversation about the critical role of memory, it raises a really fascinating final thought. The source material mentioned that the hacker wondered what it would take to get, say, a 486 MHz GameCube CPU to try inference.
Wow.
But they concluded that its 24 megabytes of RAM would be the hard wall. So given how much memory they saved just by optimizing the switch's environment,
Yeah.
what is the absolute minimum amount of RAM required to run a truly functional LLM today, even if it's incredibly slow? And what other pieces of seemingly dead hardware with their tiny pockets of RAM might be resurrected next for local AI? That's definitely something for you to mull over.